Hello everyone, I'm Miles O'Brien and welcome to the WGBH studios at the Boston Public Library. What a beautiful facility this is. Do we get a round of applause from the crowd here? Thank you. The energy is palpable here as we talk about the planets. Happy Splashdown Day. 50 years ago today, Apollo 11 was bobbing in the ocean, the Hornet was picking them up, and that amazing mission was over. I don't know about you, but I can't get enough of all of that. Might be getting close to saturation point at this point, but it is interesting that we begin this conversation about the planets, and this series should begin on this day because, after all, in the grand continuum of all the planetary expeditions that have brought us closer to our own solar system and taught us so much about the planets and the objects around us, Apollo 11 and the Apollo missions fit into that. They just happen to have people on board. I think there are probably a total of about 250 robotic missions that have occurred over the past 60 years or so, which is amazing when you think about it, the amount of information that we've gleaned from it all. And we've now completed a complete tour of the solar system. New Horizons kind of checked that final box as it went by the, well, former planet of Pluto. We could have a discussion about that later if you like. But this film, which premieres tonight on PBS on Nova, is absolutely spectacular. It's high gloss, high budget. It's a little bigger budget than I get when I do my films for Nova, but that's okay, because we're going to love it and enjoy it. It's the most spectacular animations and images. When you couple the images that are real, the animations, plus the amount of information we now know about the planets around us, and you add that all together into these 5 pieces, and you're going to walk away stunned and impressed and a lot more knowledgeable. We do know this, it has the potential to draw a pretty big audience. I don't know how many of you are out there right now, but when it streamed in China, get this, the number of people watched, 200 million. How would you like ratings like that, folks? And 200 million people watching. So I'll tell you what, I'll do a quick introduction of our panel here, and then we're going to show you a quick trailer to set the whole thing up. On the far end is Chris Schmidt. He is the co-executive producer of Nova. Seated next to him is Dr. Sukrit Ranjan. He is the Skoll postdoctoral fellow at MIT, or one of them, I suppose, or is he the only Skoll one? The one and only Skoll guy. And Dr. Anjali Tripathi, who is an astrophysicist at the Harvard-Smithsonian Center for Astrophysics. She's actually featured in the film. You'll see a little bit of her. And we're going to talk about the planets, right? Great. But first, let's take a look at the trailer.
This world is slowing down. How can I fight it? How can I?
You know, I used to have this, when I worked at CNN for many years covering space, and we used to have this joke, you know, we'd call the library at CNN and say, do you have that footage of the Big Bang that we can use again? But actually now we can do this. We have the technology. Chris Schmidt, let's talk a little bit about the backstory on all this. First of all, this was BBC Studios is where this all began, and so much good science and programming in this realm comes out of the BBC. Tell us the story, kind of the origin story of this film.
Well, it began about 4.5 billion years ago. So, you know, Nova, we partner with a lot of really world-class filmmakers and production studios. And, you know, one of the most storied and respected production entities in the world for natural history is BBC, right? So 2 years ago, BBC Studios began working on a proposal to produce a 5-part series, kind of checking in with the history of the solar system based upon what we know now, after having, as you said, kind of made a tour. I think that, there have been plenty of series about solar system and planets before, but what was unique about this proposal was that there was a desire right away to, number one, use as much as possible the actual imagery and actual data sets that have been brought back to us by all the probes, combine them with the most cutting-edge cinematic style CGI graphics, and then tell the stories of the planets not in a kind of a linear encyclopedic way, starting at the sun and moving outward, but telling them within the context of the story of the solar system. And one of the things that emerged really quickly in putting these shows together is that we found that each of these films kind of tells a unique story. I mean, I've sort of been joking, but it's not really a stretch to say this is not like just a march through the solar system. This is 5 completely independent films that are stories of love, hope, loss, betrayal, second chances, starring a rogues gallery of celestial objects, really.
So you've turned it all into a soap opera.
Absolutely.
Fantastic. Well, it's reality TV.
Absolutely.
At a different scale.
Absolutely.
So tell us a little bit about, and by the way, I neglected to say up front, we are entertaining and would love to have you participate if you're out there in Facebook Live Land or here locally. So if you have questions, start feeding them to us if you can, and we'll start curating and collating and injecting that into the conversations. Chris, what's interesting to me about this is, the animation just, blew me away. And of course, I'm just doing the budget in my head thinking, oh my gosh, how did they do this? But what's really impressive to me is how seamless the animation is with the real stuff. You almost can't see where one picks up and the other begins. Give us a little bit of the technical prowess that made this possible.
Well, it's really interesting because, you think of CGI as being images that are made 100% in a computer. And what's really fascinating is that the studio that made the animations, they're in London, named Lola, what they did was they based a lot of these images that extend beyond what we see from the space probes by live action cinematography and effects, with graphics sort of embedded and worked within that and on top of that stuff. So, for example, not to give away any trade secrets, but you'll see landscapes in Mars that were filmed actually in Jordan, and in very red desert environments that look eerily similar, in some ways to some of the landscapes in Mars, or Iceland as stand-in locations for some of the more frozen desert worlds. And the advantage of doing that, not only does it make the graphics and the images richer and more true to life, it also really reinforces the fact that all of these planets kind of have the same basic origin story, and they're all sort of made out of the same stuff at the beginning. And the big question that we revisit over and over and over in these films is, what happened next? Why aren't we looking at 8 planets that are all the same? And have these planets always been in the same places, doing the same things since the beginning as they are today, and where are they headed in the future? And so I think that to try to find the dividing line between some of these images and the actual NASA stuff is not easy, and I'm not going to give any of it away, but...
Well, so is it true that the Pluto scenes were shot in Boston in February? Is that right?
Absolutely.
Yeah, okay, yeah.
Absolutely.
Okay, I had a feeling. But no, so now I'm going to be really looking on the lookout for this. But I'm curious, how much artistic license did you allow? How much did the scientists come and say, no, that looks a little too much like Iceland as opposed to whatever?
So look, there's always some artistic interpretation, but we have one great thing going for us, which is, despite the fact that we've been to all these planets, we still don't know a lot. There's still a lot of questions. There's still a lot of competing theories about how this became like that, or how Mercury got where it is, et cetera, so that we can be working to tell truthful facts as best as we know. We can kind of entertain or favor one theory over another to suit the story, and we're not really crossing any boundaries. But NASA has, as you know, NASA has a long history of taking the raw data that they gather and embellishing it, in a way that makes it more user-friendly and understandable for the viewers. False colors and things that emphasize various aspects of a planet or whatnot. So we're just in that tradition. I
still run into people who are upset about the false colors and the nebula shots from the Hubble, and it's hard to get them past that. But anyway, who's the real talent behind this? I mean, This
Nemo.
of course, aside from you, Chris, who is the genius that made this possible?
Right. So the original commissioner was Andrew Cohen, who was the head of science programming at BBC Studios, which is an independent production entity. They're not part of BBC anymore. And Gideon Bradshaw was the showrunner, the executive producer of the entire series. And they assembled a team of filmmakers and editors and graphic artists in London and worked with us here in the US to find people like Anjali to put into the film to tell the story. So I mean, it was a big team over many years.
And once again, we invite your questions and comments as we go along here. And the website, by the way, is pbs.org/planets if you want to check that out.
And also you should note that the series premieres tonight at 9, but you can binge it. All 5 episodes will be streaming at the same time.
Yeah, it's a binge-worthy thing.
It is.
And I think no added charge to the viewing public.
Absolutely not.
Is there a better value in entertainment?
There is not.
So this idea of, the logic, the kind of the go-to thing would be kind of imagining the Voyager tour, and we stop at this planet, stop at in 8 parts, or however you would divide that. This idea of trying to create a narrative, almost a kind of certain amount of drama, was that difficult, or did that kind of just land in everybody's lap after they all looked at it?
It depends. In some episodes, it was a little more challenging than others. I mean, we know there's some planets we know a lot more about than others, right? And the histories of the planets and the histories of their formation and their evolution, a lot of that is based to some extent on computer modeling, which has only gotten better and better, not only with the increasing power of computers, but also just with the more data that we bring back and we understand, more about various all the planets and other objects in the solar system. But I think that when I think of, for example, one of the most surprising episodes is the one that'll be on tonight at 9 o'clock, called Inner Worlds, right? Which Inner Worlds, strangely, looks at Mercury, Venus, Earth, Mars, and Titan, which is a moon of Saturn, which is not an inner world. And it turns out that film, the story of that film becomes the story of change and how the divergences between the 4 inner worlds in today's terms is partly due to the changing influence of the sun. And when we look way out into the future, the sun's changing heat profile and size is going to have a big impact on the outer planets. So we're able to tell this kind of surprising story rather than just march through the solar system.
All right, well, I think you've segued us perfectly to the first clip we're going to see, which is about this very fact, a little piece of it. Let's roll that video, and then we'll begin the conversation with the really smart people here, not the TV guys.
Nearest to the young sun, 4 worlds form, each endowed with ingredients for life.
There are a lot of places in the solar system where environments could be habitable.
4 stories with surprising beginnings.
This was quite a surprise and immediately told us that some of the older ideas of how Mercury formed could not be correct.
Venus once may have had global oceans, but as the sun became warmer and warmer, the surface temperatures on Venus heated up.
The orbits of the planets and their current locations have changed over the history of the solar system. So where things are today doesn't mean that's necessarily where they formed. They could have and probably did move from different locations to where they are now.
Their destinies diverging until only one remains hospitable.
Life as we know it depends on liquid water. Only Earth has had that ability to retain liquid water over its long history. That is what's remarkable about our planet.
But for how long?
We have to realize that as stable as we think the sun is and as permanent as we think the habitability of the Earth is, it's not that way.
As our sun destroys our planet, a mission to an outer world reveals a new hope.
I believe that we live in a very fertile universe. And of course, we won't know until we make that discovery. But if I had to bet right now, based on what we do know, I would place money on the idea that this universe is full of a great number of habitable worlds.
All right. it's really exciting stuff. It's also it's a little bit depressing when you start talking about the sun gobbling up the Earth. You know, I mean, I guess that's not going to happen anytime soon.
You've got a few billion years before you have to worry too much.
Put that low on the worry list right now. Tell me, I know you have said, in this whole concept of change. Certainly, we look around in our celestial neighborhood, and we see Venus, and we think about what the ravages of climate change and global warming, and you look at Mars and what happened, what made it so dry and cold. I know you've said before that Earth could be on its way to becoming more like Mars.
Right.
Tell us about that. This idea of atmospheric escape is a fascinating concept. I didn't know we were leaking.
I mean, so I'm originally from California, where we have earthquakes. And so there, the concept that the Earth changes, we are very comfortable with. Here in Boston, we have less to worry about along that axis. But wherever you are on the planet, we have a Jenny Craig plan going on. We've got weight loss because the atmosphere, these light gases that we put into balloons and all these other things, it doesn't take very much to pull them off from the gravity of the Earth. And so actually every minute, hundreds of pounds of hydrogen are escaping into space. And a few pounds of helium. It's why helium balloons, you should be careful with them. And so it's something that it happens now at a slow rate, but as the sun, it increases the flux here on Earth. That's just going to turn from a trickle into a deluge.
Well, so it makes me think, wouldn't it be great if we could have the greenhouse gases do that, right? That would solve a problem. But in the meantime, as we lose our hydrogen and helium, over the long run, what does that mean?
Right, and so, hydrogen and helium escape rather than your CO2 and these other things because they're really light, and so they can go off into space. So if you had water and that's splitting up into hydrogen and oxygen, right, what you end up having is the hydrogen leaves space and oxygen, right, rusts us, and so we become sort of a dustier red, and so that's why when we think of Mars, right, you see this red oxidized planet where it definitely had a wetter past. And so it's probably not always as red as it is today.
So what are the current leading theories on this? Is it the intensity of the sun that has changed over 4.5 billion years, or has the orbit perturbed in some fashion? We think of things as being constant, but that's in our time frames, which are minuscule relative to the universe. Why is Mars the way it is now, do we think?
So I think Mars, right, it's such a fascination, right? I mean, I worked on the Mars rovers and the Mars Reconnaissance Orbiter, and there will be, I think, Mars missions for all of time because, you think about how back in the day with the Viking missions, we poured chicken soup on the surface, right, and to see what would happen. And so understanding its future is something and its past is something we really don't know. But one of the recent NASA orbiters, the MAVEN mission, which is, I think, featured in one of the films, talks about how that process of atmospheric escape has happened because here on Earth, a lot of the gases are sequestered in the rocks, right? So they're locked into the ground. But on Mars, it doesn't have a magnetic field. It's had this smaller world with a much smaller force of gravity to hold on to its atmosphere with. And so therefore, you have to wonder, did things go into the rocks or did they escape into space? And the MAVEN spacecraft has in fact been seeing that actually a lot of it is going off into space. And so with what we know now, extrapolating backwards, probably more happened in the past.
So, when we think of going and sending a probe to Mars or name the planet, we think about learning about it.
Right.
But how much do we learn about us when we do this?
I mean, we use everything to learn about our own planet Earth, right? When meteorites land on the surface of the Earth, I mean, you were talking about Apollo earlier. Back in, 69 or 68, the Allende meteorite landed in Mexico, right, in the town of Allende. And all of the labs across the country were so excited about this because they said, oh, we can test our equipment for moon rocks on this meteorite. And actually, it turned out, I'm very biased as someone who studies planet formation, but it was more interesting because what was found in that meteorite, it's a chondritic meteorite, is actually the same material that went into forming the solar system. So you get these gifts from the heavens on the Earth to learn about forming all of the planets, including our own, whereas digging down isn't going to get us there.
So Mars and Earth have been swapping rocks for a long time, right?
They have, yeah.
And I remember having a conversation with Steve Squires about that, the guy who gave us Spirit and Opportunity, legend in Mars exploration. And he said, it's quite possible that we're all Martians, that the life could have come from Mars to here. Is that possible?
I'm not familiar with life and where it comes from, and I feel like that's a mystery that's maybe above my pay grade.
Yeah.
But I think that we don't have the full story all hammered down. I mean, one of the reactions I got to this film was why are there so many questions? Why aren't there more answers? I want answers. And I think it's a beautiful testimony to the fact that as we learn more with these spacecrafts, we also realize all of the other questions that we don't know. And so I encourage all of you to come and join the adventure and be scientists like us, because we need all the help we can get.
Yeah. Well, it is kind of interesting too when you think about how really in this era, everybody gets all the data at once, whether you're the scientist or you're the person at home. It's kind of empowering in a way that everybody can participate, at least at some level, right?
Absolutely. I mean, one of the most exciting discoveries, so we're going to step out of the solar system for a second, is because when you look up at the night sky, almost every star is its own sun for its own solar system, right? There are hundreds of billions of extrasolar planets out there. And the thing is, we have opportunities for you at home on your computer to go to the Planet Hunters website, and you can help discover planets on your own, right? The fact that we have data from the Kepler spacecraft and these other missions available to not just scientists, but also the public, I think is really empowering and exciting.
So now, at the end of that little clip, David Grinspoon was saying, well, I think there's going to be, it stands to reason, there's going to be millions of these. Or I don't know if he said millions, but lots. What's your take on it?
I think life is definitely out there. I don't know if it will look like us, but certainly the sorts of things that might be growing in my bathroom if I'm not too careful on a given day, I think are probably out there, and we'll definitely find it within our solar system before we find it in these more distant worlds.
So, of course, we are bound by what we see here and how we determine what life is, right? So, of course, we assume it's carbon and water and nitrogen, all the things that make us. But there could be a whole separate kind of life that we don't even understand, right?
Of course.
We don't have the tools to look for that? Is that basically the
you
answer
have
to that?
know what you're looking for, right? And so if you don't know what that looks like, it's impossible to tell if that's what you've found. And so I think, we think about water as the ingredient for life. We think about carbon-based life forms. That isn't to exclude the possibility that there's other options out there, but I think that's where we start from. And once we conquer that, then we can sort of get a little bit more advanced.
Yeah, maybe there are creatures that love methane or something.
Of course.
Right? Yeah, it's possible. Once again, if you have questions, comments, we'd love for you to participate here on Facebook Live. The website is pbs.org/planets, where at 9 p.m. tonight, if you don't want to watch it on television, you can go and stream the whole 5 hours. You can just get the popcorn out and watch the whole thing tonight and let us know what you think about it. So participate with us right now and get some questions in, but by all means watch the big event later tonight, 9 p.m. Eastern. I guess that's 9 p.m. local, right, wherever you are. Is that right? Or is it like 8 p.m. Central? I don't know.
This is a lot more complicated.
This is actually more complicated than doing a mission.
8 Central, 9 p.m. West Coast.
Yeah, I don't know.
Stream it
at 9 Eastern. All right. So I tell you what, let's move into the Mars chapter and talk about that, because you mentioned that was kind of your first taste in this whole thing. So let's take a look at Mars. Mars was once, we now can say categorically, it was once warm and wet, and now it's cold and dry. And understanding what may or may not remain, or what might have taken hold in that process, is a key part of this film. So let's watch for a minute.
For hundreds of millions of years, Mars is a water world, rich with the building blocks for life. Rains fall, rivers run. And in the northern hemisphere, evidence suggests water collects in a vast sea, bigger than the Arctic Ocean, that covers 1/5 of the Martian surface. The red planet was once blue. But it didn't last.
The fascination to me about the early warm, wet Mars is not what happened, although that's an interesting question. Why did it dry up?
The billion-dollar question is whether or not Mars actually originated life before all the water was lost.
How far along did it get? How far along did the process go, and did it go long enough that life could have taken hold there?
All right, so we have a question that just came in from Elizabeth Traxler on Facebook, and we'll take this to Secrete, since this will get us, or actually, maybe you should do this one.
All right.
What is the current hypothesis for the life expectancy of Earth?
Oh man, there are so many things that could bring us down. But I think, what we think about, like I said earlier, is a few billion years, because the sun, like any star, has its own life cycle that it's going to live. So it's going to change over time. So over time, it's going to become a red giant. So it's going to swell. The core is going to heat up. You're going to get the outer layers cooling. But actually, here on Earth, it's just going to seem hotter because that distance is going to go down. So, you're going to get atmospheric escape happening just en masse. So it's going to get a little bit redder here on Earth. And then eventually, I'm afraid the prognosis for Earth is not great. The sun is actually going to engulf us. So that's the far future, but we don't have to worry about that today. Hopefully, you can all sleep soundly.
Yeah. Of course, going to Mars isn't going to solve the problem.
Going to Mars is not going to help
Pretty much
us.
the solar system is going to be a problem.
That's right.
Without the sun, there's no real solar system.
That's right. I mean, and this is, you were talking about Pluto earlier, but this is the problem with planets, right? Because planets, by definition in the solar system, have to meet 3 criteria. They go around the sun, they're round, and they've cleared out things 50% of their size. So if we didn't have the sun, actually, we wouldn't be a planet either.
All right, so Secrete, let's get back to Mars here for a minute. What's your take? There's been so many tantalizing clues, and even some very recent, about the presence of liquid water underneath, and kind of a liquid aquifer, underground lake, if you will. And then there's these interesting sort of seasonal methane spikes, which really are difficult to explain in the absence of life, right? So what is your current thing? Is there something going on there? Is there some sort of microscopic life form that we haven't detected just yet?
Well, I think those are really great questions to highlight. And I think for me, one of the most interesting meta points to raise is that the most interesting part of Mars to me, in terms of life here, is the subsurface. The subsurface, in terms of following the water, it's where you might have enough of the geothermal heat left for water still to be liquid. So you might have habitability. You might have gradients in the form of hydrothermal systems that could sustain microbial communities. So I really would like to land a drill on Mars and just drill down and see what we can find. In terms
Not an easy thing, though. When you start getting drilling stuff to...
If you're assuming you're being ethical about it, not an easy thing. You could drop a really large rock and excavate it that way, and then do do spectroscopy from orbit of the results. But that's not considered to be...
Or if they found oil there, somebody would probably stay there.
Yes, we could freedomize Mars.
Yeah, we go drill that for sure. Anyway, so what's your guess? I think we can say pretty categorically, correct me if I'm wrong, wherever there is liquid water on this planet, wherever, you find life, right? Isn't that true?
Not quite. Actually, there's a substantial amount of Earth that is known to where we think there's water, particularly in the deep subsurface, where we don't know whether or not it has life. So that's not something that we can rule on firmly one way or the other. However, it is very tantalizing that at least in superficial systems, wherever there is water, there does seem to be life. The key ingredient seems to be availability of gradients to power metabolisms.
So we know there's liquid water beneath the surface of Mars. Mm-hmm. That raises the chances significantly that there might be current life there. So put that aside for a moment. What about ancient life? You think that, is there much, can we tell? We haven't found a fossil on Mars despite what happened in the 90s and the little, that little fossil, which wasn't a fossil. But the fact is there some, everything leads you to believe that this was a cushy birth for life. The question is, did it take hold, right? Is that the real question?
I think the film, and you pointed that out really well, that Mars, early in its history, could really have been a very appealing place for life. And I think because of the exchange of rocks between Earth and Mars, it doesn't matter which planet life started on. I could very well see it taking hold on either object. I think the really compelling thing about Mars...
You're going with the Martian theory.
I'm not going with it. I'm saying it's not ruled out.
He's a good scientist. Be careful.
I think the compelling thing about Mars is actually the problem. The Martian surface is a terrible place for life today because of the absence of liquid water, but that actually makes it an amazing place to go look for evidence of past life. We have very few time capsules from ancient Earth because of water activity and weather and things like that. They just destroy all the rocks. We get almost no information. But on the Martian surface, you might have we know that there's billions of years old rocks just sitting there, unaltered. And so those are messengers from the past that we could really use to inform both our understanding of what early Mars was like. You could have really well-preserved fossil evidence of life on Mars if it was there. And you might even have well-preserved terrestrial rocks. So it might be ironic. The best measurements we might have of what early Earth was like 3 billion years ago, 4 billion years ago, might come from when we send people there, they collect rocks and they find an Earth meteorite, and we come back and analyze
Wouldn't that be interesting? Yeah. Interesting, ironic turn. I know you, I know historically Mars, back in the day, had a lot of shallow oceans, I guess you'd call them, or ponds. I don't know what the correct term would be. Shallow bodies of water, we'll say. And I know you've done a lot of work where, I think we all imagine life magically happening in the ocean, and we kind of crawled up one day, and all of a sudden you get Boston. So, but you have done some work where you think maybe the life actually formed in shallow ponds here. Is that right? Explain that theory.
Yeah, sure. So I think one of the really interesting questions in origin of life research is what are different venues where these kinds of chemistries can happen that can put together those molecules, the carbon, the hydrogen, the oxygen talked about, into biomolecules that might help power the emergence of life. I think there's a lot of really great experimental work and theoretical work that's going on in this. And I think the jury's still kind of out there. I think that there's a lot of really interesting chemistries that work in the ocean. There's also a lot of really interesting chemistries that could work on land. This goes all the way back to Charles Darwin, who wrote in a letter to his friend Hooker in the 1870s. Well, maybe there was a little pond, it was full of amino acids, little salts and stuff like that. Maybe they all got together, did a little jiggy, and something popped out. And realistically, the meta picture of the origin of life is still essentially that, whether it's in the ocean or whether it's on land.
And one of the key, nitrogen is a key, right? Isn't that a big
nitrogen
part of this?
is really interesting. The problem with nitrogen on Earth is that it's N2. N2 is a great gas, does a lot of wonderful things for you. You can use it for pressurizing all sorts of systems, for example, but it's also really stable. It's hard for life to break it apart. That's one of the main, and one of the things that life figured out to do that was really clever is break it up and put it into a molecular form that we could use. And that's actually the main ingredient in fertilizer is fixed nitrogen. It's hard to figure out how life started doing that initially because you need a complicated enzyme for that. One mechanism people have invoked is maybe lightning split apart that nitrogen and made it rain down. It's a lot easier to get high concentrations of nitrogen that way, the kind you would need to get life started if you were in a pond compared to the ocean. So if you want fixed nitrogen in particular, ponds are a better place than oceans.
So let me ask a question. What about hydrothermal vents? Do those provide enough energy for that kind of a reaction? Because I know that on Mars, the name of the location is escaping me, Ecus Mare maybe, there are some mineral deposits that seem indicative of ancient hydrothermal vents, much like the black smokers in the very deep oceans where there's volcanic activity essentially and there's life, these are miles below the surface of the ocean, no sunlight at all, no photosynthesis, but lots of life because of all the energy that's coming up through the superheated water. I mean, can that power some of those nitrogen bond-breaking reactions?
That's another really great question. I think hydrothermal vents are absolutely fascinating systems. They're these really exotic systems where you have the interior of the Earth coming into contact with the surface. You have all these insane gradients. You have all this exotic life that thrives there. And what's really appealing about it is that this can exist down in the bottom of the ocean. The surface can be having whatever catastrophes you want, but down at the bottom of the ocean, it's going to be safe and stable. So I think that hydrothermal vents are an incredibly habitable environment, and they're a great place to look for extant life. Whether they're a great place to look for the origin of life is, I think, a little bit more out there. In particular, if you look at the question of how do you split apart that nitrogen, they have a lot of energy, they have a lot of heat, but they don't have enough to split apart that nitrogen. So if you're trying to access the nitrogen, they're not as good a place for that particular thing. But they are super habitable and really fascinating environments.
All right, so Creed, as the catalog of exoplanets grows, and it grows quickly, it's hard enough for us to sort of come to any sort of conclusion about life or not on Mars. How are we going to solve that one? There's no easy life detector looking at something that far away, right?
It's a tough question, but I think we're helped there by the fact that, as Anjali mentioned, we're blessed by the fact that the universe has gifted us a cornucopia of potentially habitable objects. And one of the challenges in our solar system is that we seem to be Goldilocks. We seem to be we seem to be the only object where it seems to be easy for liquid water and life as we know it to thrive. But the universe it turns out that the stars beyond our own seem to be full of such objects. On average, I think 1 in every 5 stars has a planet like that might be similar to our own. And so I think the really appealing thing is that it's hard to look for life elsewhere in the solar system because it's really a tough place for it to exist. It's going to be trace. But I think once we develop the eyes to do so, once we have the tools to look at stars beyond our own, we might get lucky and find a thriving biosphere very similar to our own that's easy to detect.
Wow, that'd be a lead story for sure that day. Okay, we do have a microphone in the back somewhere. Where is it? If anybody in the audience would like to weigh in, this would be a good time. Or we can, I'll tell you what, we'll do this clip and then we'll get that queued up. And of course, those of you at home, we'd love to hear your comments and thoughts and questions on Facebook Live. And of course, don't forget 9 p.m. Go to pbs.org/planets. And just binge watch all night long, and let us know what you think about the whole thing. So let's, one of the things that happened, I said earlier, I think that there are 250 robotic missions that have been sent out over the 60 odd years since Sputnik. It's extraordinary. And when you think about all the engineering that goes into that to answer these questions, it's certainly a remarkable thing. And what happens inevitably in these missions is they become like the children of the people in mission control. And certainly this was the case for Cassini, which, as you know, had about a 20-year run, and about 13 years of that time was orbiting around Saturn, exploring its rings. And then, of course, in September of 2017, met its demise. And that's an interesting chapter in this film, so let's watch for a second.
Cassini survives its approach to Saturn intact and continues on towards its demise.
We're out at JPL watching the signal coming from the spacecraft, and there was a spike. And it went away, but it seemed to come back, because the spacecraft hadn't been told its life was ending. And so it had been programmed to keep in touch with the Earth. So it moved itself.
Okay, we call loss of signal at 115546.
The last command that my colleagues uploaded to the spacecraft was a list of the 200 or some scientists and engineers that had been involved in the development of one of the instruments, which means that as Cassini was literally disintegrating, in its computer memory was a final thought of home. And I think that's just a tremendous, tremendous thing.
You've just heard the signal from the spacecraft just go on, and within the next 45 seconds, so will be the spacecraft.
And then it lost control, it began to tumble.
The world that had borne witness to some of the greatest dramas in the solar system's history consumes the craft that has given us its remarkable story.
Congratulations to you all.
I was supposed to call end of mission. Thanks and Godspeed, Cassini. I couldn't get the words out.
There was some applause, but mostly people
were just looking at each other. It was so sad. Really, really sad.
It's still hard.
Makes you want to cry, doesn't it? You've been involved in these missions. It becomes very personal, doesn't it?
Well, I remember being back at JPL in 2004 when Cassini just got to Saturn, and there it was the early terror for Saturn orbit insertion, because you lost contact while it was going to go through the rings, and you hoped it was going to make it out the other side, and you felt this tug on your heartstrings. But even at that point, it was less than, in 2017. You would watch it grow up, you would watch it as an infant, and it sent back all of these amazing, just, I don't know, it sounds trite to say, but earth-shattering pictures. And so you had nothing but love and respect for it, and was sad to see it go.
Chris, we were talking earlier about how much we've done in 62 years since Sputnik. It's quite extraordinary. But yet we're just getting started too, right?
Well, so one thing I wanted to say about Cassini is that self-destruct, dive into the vast clouds of Saturn was an intentional act, because there was a concern that if Cassini's fuel was allowed to run out and it was no longer able to be guided from mission control, there was some chance, even small, that it might crash land on Enceladus, one of the moons of Saturn, which is shown to be a location where there could be life, believe it or not. It's a moon that is It's covered with a ball of ice. It's covered with a layer of ice. There's clearly liquid water below the surface. And the reason that we know that is because every now and then that water erupts into space in plumes of water. I mean, it's actually potentially possible to fly a spacecraft through that with a detector to pick up signs of life. And you could pick up, the microbes in that water itself. So the mission control specialists realized that once, and this was a surprise, this was a discovery that Cassini made when they observed these plumes. And they determined that there was no way that they were going to risk having Cassini crash, because even though you think of a spaceship in deep space for 20 years, we know now that certain kinds of very, very small life forms, bacteria, tardigrades, can actually survive in that environment and be dormant and potentially be brought back to life. There's been an experiment bolted to the side of the space station with microbes basically exposed to space and radiation for some long period of time, and then they're brought back to Earth and they come right back to life. They're like sea monkeys, right? And so the thing to me, when we started working on this series, the thing that kept blowing my mind was when you think about the fact that in just 60 years, you go from, Sputnik was 1957. We had Ranger, first craft to land on the moon in 1961. And in 1963, just 6 years after Sputnik, the Soviets are chucking spaceships at Venus and trying to land on Venus. It's just sort of mind-blowing, right? And so we've covered that, we've written sort of a first chapter, but to me, the thing I always think about is this continuum between basic scientific discovery on Earth that then leads to the questions that the engineers and the scientists are asking about other planets. So if imagine you're going to spend billions of dollars and you're going to send a probe to another planet that's billions of miles away, and you basically are allowed to pack 10 pounds of luggage, let's say, or 100 pounds of luggage, some instrument or some instruments. Like, how would you even know what to stick on that thing? Are you going to be looking for a magnetic field? Are you going to be looking for specific gases? The only way you can know that is if you've learned and understood how Earth works and how basic physics and chemistry and geology works here, and that gives you the question. So we could say we've gone from 0 to the end of the solar system in 60 years, but the journey began hundreds of years ago during China's heyday, scientific heyday, during the scientific revolution, during the Renaissance, when basic ideas and basic laws of physics, chemistry were being discovered. So it's pretty amazing to think of that, for me to think of that continuum.
That expression, standing on the shoulders of giants, comes to mind, right, which is what we're all talking about here. So Crete, there's a question from Facebook which is relevant to our discussion. Are there any upcoming planet exploration projects that are particularly exciting to you or anybody here for that matter?
I'm tremendously excited about the Dragonfly mission, which was just announced by NASA to be that has been selected, which will be sending a drone to Titan to study its atmosphere and its processes. And there's a couple of reasons that's so fascinating to me. One is that Titan is intrinsically a fascinating object. It's much less massive than the Earth, but it's got a thicker and heavier atmosphere than we do. And the combination of that means that if you were to strap on wings and flap your arms, you could fly there, which is always kind of nice.
How cool would that be, huh?
Yeah.
Let's go to Titan, man.
That's going to be 100 years from now. It's going to be the resort destination of the solar system.
Titan is a methane planet, right? Isn't that right? Yeah.
Titan has a lot of methane, but it's mostly a nitrogen atmosphere. It's a nitrogen-dominated atmosphere.
All right, good.
And that's another reason it's really fascinating. Is it's one of our only examples of a really reducing atmosphere here in the solar system. And building off the idea you said, one of the objects that we really want to study in outside the solar system is planets with a lot of reducing compounds of their atmosphere, because they're easy to detect and study. And the only example we have of that is Titan. So Dragonfly, I think, is going to really revolutionize our understanding of those objects and help us interpret those measurements.
The thing about Titan is, as Anjali was talking about the Earth ballooning up into a red giant, getting hotter and hotter and hotter. Well, there's a lot of water ice on Titan. So if the sun...
Methane ice.
Pardon?
Methane ice.
Methane ice. Yeah. And there's also Titan.
It's a non-smoking planet.
It is. and Titan's the only world we know of so far besides Earth where there's actually liquid pooling on the surface. Lakes, rivers, they're liquid methane, not water. But if Titan were to warm up, there's plenty of hard water ice that could melt into water. The methane could sublimate into the atmosphere. It's potentially a really interesting place. You just got to wait, a couple billion years for that to hit?
So buy your property now.
Yeah.
I think we have a question here in the audience in the back. I can't see the person, so there they are. Go ahead.
Hi, my question is for the two scientists on the panel, actually. I was wondering if you had, say, $10 billion and were in charge, what missions would you be most excited about instantiating? Would you ground-based telescopes, space-based telescopes, manned missions, robots? You going to mine an asteroid? And I realize 10 billion might not be enough.
Is it 10 billion or 10 million?
Yeah, 10 billion or billion?
Billion, Professor.
Billion.
$10 billion.
I
What are
see.
you going to do with that, right?
Sigrid, do you want to?
Oh, I would want to fund the terrestrial planet finder. So one of the I think everyone has their own pet projects. My fantasy project that I've always wanted to see fly is a telescope, an orbital telescope that could take a picture of an exoplanet and search it and take the spectral measurements that might give us a fingerprints of life. It is going to be a very expensive mission. It will not fly in the near term, but if you gave me a dictatorial $10 billion, that's what I'd put it towards.
So could the James Webb telescope, pull any of that off if that ever flies with something to block out
I hope
the
it flies.
sunshine?
After all that money spent, it better fly.
I think James Webb is going to revolutionize our understanding of exoplanets. I think it's in particular going to revolutionize our understanding of planets that are in between the size of Earth and Jupiter and Neptune, the so-called super-Earths. I think I have a lot of hope, and I think we might get lucky, and I think James Webb might be able to give us some information on rocky planets, but it'll be a tough observation. And the reason it'll be tough is just because James Webb has a finite lifetime. It has a certain amount of cryogenic coolant, only about 5-year supply, and when that goes, most of its instrument capabilities go. And we just don't have enough time to get all the pictures that we need with James Webb.
All right, Anjali, design your $10 billion mission.
You know,
You can assume it's a down payment, right? You know, so just blue sky it.
I mean, I actually get really excited about talking about the ultraviolet and what we can see, because that's something that, you know, you can't really do that from Earth. You have to go to space, right? So the Hubble Space Telescope has great ultraviolet instrumentation, but as we know, Hubble is getting old. And, you know, something like JWST is all in the infrared. We don't have, you know, state-of-the-art ultraviolet coming on board anytime soon. So there's actually even a private company based out in Massachusetts where they're trying to privately fund a UV telescope. And so if you have $10 billion, they might like to hear from you.
Why has it been hard to get funding in the UV?
Well, so I think the UV is one of these things that, for me, it's really interesting because when you look in the UV at Earth, for example, you can actually see atmospheric escape, right? You can see hydrogen, you can see this coming off. But there are so many other things that come to mind first for most folks that it often gets pushed down. And so I think as a good complement to a lot of what we see now, having just a stable UV observatory is good for studying galaxies and planets and everything in between. And, you know, that's how we learned about atmospheric escape, not only from the solar system, but also from planets out beyond the Earth. And so earlier you were asking, how are we going to detect life around these other planets? Well, the way we're going to learn about them in extrasolar planets is through their atmospheres, right? And how much you can learn about their atmospheres is very wavelength dependent. And in the UV, that's actually one of these places where you can see how extended they are, right? It's not just tightly bound. And so if you're seeing it escape into space, you're actually watching these other planets evolving too. And so I think it's just this fascinating window into, we don't even know what we're going to find, but if we just close that down, we're losing a lot.
Can I suggest you combine those so you could find habitable planets where you could get a really good suntan? I think that would be perfect.
All right,
What is
noted.
the SPF requirements? There's all kinds of questions that could be answered. All right, we have another question from someone here in the back.
Hi, I'm wondering what you guys think about innovations in rocket propulsion for the future of intergalactic travel, because right now fuel is finite and takes up such a huge portion of mass, whereas we just had a solar sail go into space, and we also have like new innovations like electrospray ionization.
So solar sails, ion engines, nuclear propulsion, what do you think is going to get us really out there? We're talking warp speed. You go first.
Okay, I don't know if we're going to get to warp speed, right? And you know, the sad truth is, for the things that we launch that will get to the planets, you know, 20 years from now, we have to launch them with the technology of today, and so we're not there yet. I mean, Juno was pretty zippy with the propulsion system that it had, but I think that, you know, no matter what propulsion system we come up with, we're probably still limited to the Milky Way galaxy, right? You were talking in the question about intergalactic travel. And I think regrettably, in spite of our best efforts, we're never going to get much further out than our own star.
There should be enough to look around at inside the Milky Way, though, right?
Sure.
Keep you busy for a while,
Yeah.
yes. All right, what do you think about propulsion issues?
I think that building off what Anjali said, I think it's going to be really tough with near-term technology to get us out there, but I think in terms of getting robot probes out there, I think right now Project Starshot is being developed. So that's being developed with private money, and it's essentially a technology demonstration, but the idea is that you could take a really small probe, something the size, maybe the size of this, you can strap it to a solar sail, you can power that solar sail with a battery of lasers powered from Earth, more on that later. And if you can do that, you can actually get up to a significant fraction of light speed. So you could fly a really small spacecraft past Alpha Centauri within our lifetimes with near-term technology. It's just that will cost a lot of money.
Nova recently did a film called Rise of the Rockets, kind of looking at this sudden explosion in private rocketry and private enterprise. The thing that you really learn really quickly, there's two things I think are personally fascinating. So all our rockets right now are chemical rockets, right? So they burn propellant. They create a chemical reaction that throws hot gas out the back end of the rocket. According to that guy Newton, you still need to throw something that way if you want to go that way. But their acceleration, their burning of the fuel is really brief, and then they coast. So if you can simply, even if the thrust is relatively low, once you get outside of the Earth's gravitational field, if you can turn it on and keep it on, you can really get moving, and you can reduce potentially the time to get to Mars to weeks instead of many months. And there are technologies that make that possible. They haven't been sort of worked out in a kind of a tested way, but there are already small spacecraft that are using ion engines. The probe was it the Dawn probe, I think, that went to visit the asteroid belt. An ion engine basically speeds up small amounts of atoms to extremely high velocities, much faster than you would get with a chemical rocket, and throws them out the back. And it's each thrust is not that much, but you turn it on and leave it on, and things can really start to move. So I don't think we're looking at hundreds of years. I think we're looking at decades before you start to see some of these engines come online for even human space flight. But somebody's got to invest in it.
And I would just add that we think about it in terms of the technological development, but also some of it is just the laws, right? Because you can't put a nuclear reactor in space.
Right.
If you could put a nuclear reactor in space, then using today's technology, we could actually just keep going for quite a while. So there are different aspects to this problem to think about.
Well, in the context of the 50th anniversary of Apollo 11, we've been talking about a sustained presence in space for humans. And a big part of this is just getting out of what they call the gravity well. Really, it's the first 200 miles that really hurt you. And once you're outside of the pull of gravity, you've got a little bit of a big leg up on
the moon.
Right?
And the moon is now, we know the moon is a great source for rocket fuel.
Yeah.
Because we've discovered a lot of water on the moon and hidden in the craters and the poles that you can just break apart into hydrogen and oxygen and then recombine as rocket fuel.
But you need like nuclear power to do that.
You do.
You do a lot of juice to make that happen. Are there any more questions here in the back? Are we? No one has any questions about this provocative?
Can I say one other thing about the gravity well? Something that I think is amazing is, so if you take the most powerful chemical reactor, like right now, liquid oxygen, liquid hydrogen, that's the gold standard for chemical propellant. If the Earth was, I forget what the statistic is, if the mass of the Earth was like 15 or 20% greater, no chemical rocket would ever be able to get into orbit.
Wow.
We are really lucky. We got in just under the threshold because the force of gravity would be too great to overcome, or for any chemical rocket to overcome that acceleration that you have pulling you back to Earth.
Of course, maybe that bigger Earth would have better chemicals. Who knows? Right?
No, there's only one periodic table, Miles.
It doesn't change, does it?
No.
Yeah. Gosh darn, science really is tough, isn't it? Yeah. So, when you look at a series of pieces like this, a 5-part series, I'm curious what your thoughts are on what the message is for people, and what do you want to communicate to people about your work? I mean, we've been deep in the weeds talking about technical stuff, but at a very high level, this has it's kind of an emotional story in a way, right? So, and I know scientists, after all, it's narrated by Spock. There's not a lot of emotion there, right? But I mean, essentially, what you have here is the story of us, and it forces scientists to get on the right brain a little bit. But I'm curious if you have any thoughts along those lines.
So I think there are two main points that I get excited about sharing with this series. And I think the first one is that the planets are changing and evolving. And so as you ask questions about it, we don't have all the answers, right? So one part of that is look at how many answers we do have from all of these amazing spacecraft and these robotic missions, the telescopes on Earth. Just look at all the things we do know. But then the second part of that is look at how much we don't know and all of that uncertainty, because I think we will never know the full story of how we got here with everything that's involved. We will never know, every inch of Mars's habitable past or not. And so I think it's that there are still going to be these discoveries, but there are going to always be even more questions. And I think understanding and getting to terms with that uncertainty, whether it's this crazy end with the sun and what that means for us, I think that's really profound, and it's great that we get to share that in all of the scientifically accurate detail and beautiful cinematography.
So there will always be work for scientists.
There will always be work.
Until the sun explodes.
It's a jobs program that keeps on going.
All right, Sukrit, your thoughts on the message that a series like this sends out, or should send out?
To me, the message that comes across is, I think, the one that's being conveyed pretty well, which is that each of the planets is a book that tells a story. And it engraved in the evidence that's in their surfaces and in their atmospheres and their subsurfaces is the incredible process they've been through, from coagulating and forming in this kind of maelstrom of cold fire as accretion happened, all the way through these dynamic events through mantle formation and melting, atmospheric outgassing, atmospheric escape, atmospheric evolution, and in the case of at least one object, the evolution of life, which then altered the atmosphere and the surface in such profound ways. So to me, one of the most exciting parts of this kind of science is learning how to read that book and telling that story to everyone.
Chris, you've been involved in this project from the beginning, in scripting and the words that were conveyed and how you conveyed it. What was your goal?
It's I think that the goal is really to showcase something, to quote Carolyn Porco, who's one of the Cassini scientists, the fact that you can take this, you can dream of and create this machine that you can send from Earth to Saturn, not knowing very much about Saturn at the time. Ask the right questions, observe, watch, think, redirect, gather data, and at the end, bring the mission to a close. As she says, it really is in some ways the best of us. It reflects the pinnacle in some ways of what who are these kind of crazy jumbles of molecules that were many or most of the atoms in our bodies once were in an exploding star or a dying star, that all of these things can come together and in a sense kind of allow the universe to look back on itself and ask questions about itself. I mean, that's pretty amazing.
People ask me why I cover space and why I'm interested in it, and that is it in a nutshell, because it brings us together. When you think about the stories that we all talk about and bring us together, they're usually pretty negative, frankly. And space is one place where we can celebrate our accomplishments in a very grand way. And this film captures that in so many ways. Congratulations to Chris, in particular, for shepherding it through. Congratulations on your role. Sukrit, thank you for being in here. We'll put you in the next film. But we appreciate you being a part of this talk today. We want to thank our funders, PBS, the Draper Laboratory, who made this NOVA series possible, the BBC studio. Wow, what a great studio this is, too. The WGBH studio at the Boston Public Library has been fantastic. Check out The Planets Tonight, pbs.org/planets. You can start streaming, get the whole 5 episodes right now. You can watch it the old-fashioned way on television, but either way, you should be a part of this. It's absolutely must-see TV.
Let us know what you think. Reach out to us on Facebook, Twitter. We're standing by. We want to hear from the viewers.
All right, from the Boston Public Library, the WGBH studios, I'm Miles O'Brien, and this is the Planet team. Thank you so much for being a part of this, and tune in tonight.